Good afternoon, everyone. Hope you can hear me properly. Okay, let's wait for 2 minutes. Let's all of them join, and then we'll start. Uh, like everyone joined, so let's start the section for today. So, good afternoon, everyone. And do you remember what we discussed in the last section? Yeah, we discussed what? We discussed about entropy and how we can write entropy in different forms, all these things, right? So, what did I say in the last class? What will be discussing in this class? First thing is we'll be seeing what happened in the previous class, small recap, and then we'll be seeing some different expressions of entropy, and then we'll be going to Gibbs free energy. Okay. No. What is entropy is equal to? Entropy is nothing but what is the reaction happening? Like let's say from normal solid state to liquid state. What is happening here? The molecules are going far from each other. Nothing but entropy of the molecules are increasing. That was discussed in the last class, right? And what was the expression for delta S? Delta S is nothing but delta Q by T, right? Change in heat of the quantity at constant temperature. This we have seen, right? So we'll be using this, and we'll be deriving again some new equations based on this. So if you see, we know that delta or dq or delta q is equal to du plus dw. Nothing but whatever heat we are providing to a system, that will be used to increase in the internal energy, that is u, or to do some kind of work, right? Any of that will be happening. The energy will be transferred from one form to other form, but we cannot create it nor destroy it. From the first law of thermodynamics, we have seen that heat is equal to change in heat is equal to change in internal energy plus work done by a system or work done on the system, right? No, we'll be using these two equations and we'll be deriving different cases. First thing, what is isothermal process? Tell in the chat. Huh. Isothermal process is nothing but constant temperature, right? Isothermal, isothermal is nothing but at constant temperature. Isobaric, what is isobaric? Nothing but at constant pressure, okay? Constant pressure, we'll call it as isobaric. If it is isochoric, nothing but at constant volume, right? What was one more thing other than these three? One more is adiabatic. No, what is constant in this thing? Constant heat, constant Q. Okay, these are the four conditions we have seen, and we'll be seeing how entropy will we can derive entropy in these four types of conditions, or what is the mathematical formula used so that we'll get entropy by in these four kind of different situations. Okay, now first thing, let's see entropy change for an ideal gas in thermodynamic process. For first law, from first law, you have seen that dq is equal to du plus pdv, nothing but dw is nothing but work done pdv. Okay, just we substituted that part here. Okay, now you know ds is equal to dq by dt. So sorry, dq by t. No, just we are substituting the dq formula here itself, so that we are getting du by t plus pdv by. Okay, now at constant volume, du is nothing but what? N cv dt, right? And let's rearrange the p by t formula also, where you know pv is equal to nr, right? Now what is the form you are seeing? P by t, right? P by t is equal to what? nr by v. Just we will be substituting these formulas in here. Just substitute these two cases in the formula. Okay, then what we'll be getting? ds is equal to, in place of du, n cv dt by t plus, sorry for that. Now if you see here, if you substitute that n cv dt by t plus nr by v dv, just we substituted p by t, right? So what is p by t is equal to nr by v. Just we substituted that form here, nothing. And du is equal to n cv dt, that we substituted here. These two expressions we have substituted in this. Okay. Now, after integration, what we'll get? Delta S is equal to NCV at specific heat is a constant, right? At constant volume. So that's why these will be coming out, and we'll get the form as ln T2 by T1 and nr ln V2 by V1. Okay. This is the new expression to derive entropy by using temperature and volume terms. Okay. Specific heat, temperature, and volume terms. Okay. Now, whenever we use adiabatic expression or isothermic or isothermal expression, so we need to see which of these units can be removed, or which of these units are constant, so that they can be, there is no change and those units can be removed. So we'll be rearranging the formula based on what are constant and what are not constant. So this is our main formula. Try to remember this. And if you want to express it in pressure terms, nothing but NCP ln T2 by T1. And as you know, pressure is inversely proportional to volume. V2 by V1 will be in case of P1 by P2. Exactly opposite. Nothing much difference here. Just if you remember this formula, the rest of the entropy forms can be given whenever isobaric is asked, or isochoric or isothermal is asked. Okay, just how to rearrange we'll be seeing. Clear until here, or you have any doubts, you can text in the chat. If you have any doubts, just text in the chat. Okay. If you don't have any doubts, let's move then. So in isothermal process, for a reversible or irreversible isothermal expansion and contraction for an ideal gas, how to express entropy? First, we'll be seeing a irreversible process, let's say. No, delta S system is equal to nr ln V2 by V1. What is constant in isothermal process? You know that in isothermal process, temperature is constant, right? Temperature is constant. No, if temperature is constant, as we know, if temperature is constant, internal energy of the molecule is constant. That is, EU is constant. It is not changing. So what does that mean? Where we have substituted the du term or ncp or ncv this whole term will become zero as temperature is constant, du is constant. That means the change in internal energy will be zero. Okay. So that's why we'll be writing regarding delta S is equal to nr ln V2 by V1. Are you clear with this form? Just you need to see what is constant and what form we need to remove from the original equation. Okay. If they ask you for surroundings, nothing but delta S surroundings is equal to minus delta S system. Like what is the heat lost by the system or heat gained by the system? That is the same change which will be occurring. Uh, sorry, how much entropy lost or gained by the system will be uh, resulting in the opposite form in the surroundings, right? If heat is absorbed, entropy is increased in the system, surroundings entropy will slightly decrease. But you know, as surrounding entropy is very high, we cannot see that naturally. No. Second thing is isobaric process. No. In isobaric process, what is constant? Pressure is constant. In isobaric process, what is constant? Pressure is constant. Now, if pressure is constant, then which term can be neglected or what is the new term you can introduce here? Now, as you know, dq or dq is equal to du plus dw. The same thing where at constant pressure, delta H is also equal to du plus dw. Nothing what we can write as dq is equal to dH. Okay. Apart from this, where at a constant pressure, where the work done is also neglected here, and we are going to write it as delta S system is equal to ncp ln T2 by T1. Okay, not a big difference. Where delta H at constant pressure is written as Cp dt, or if you at n number of moles, ncp dt. Here also same thing for surrounding. If you ask minus delta system, delta S system. No. In isochoric process, what is constant in isochoric process? Volume is constant, right? Volume is constant. Now, if volume is constant, what happens to work done? Work done will become zero. So again, what happens? We'll come back to what is du at constant volume. That is nothing but Cv dt. So it will be Cv ncv delta T will be represented here, not pressure. Okay, where du is equal to Cv delta T. That is substituted, and we'll be getting the final form as delta S system is equal to ncv ln T2 by T1. Nothing more. Here also same thing. If you ask change in entropy of the surroundings, nothing but minus of change in entropy of system. That gives you change in entropy of surroundings. Clear, simple. Only the system questions you need to remember here. If you know the how to calculate system, the opposite will be happening for the surroundings. Okay. No. Final thing, that is adiabatic process. What is constant here? dq is constant. That is heat itself is a constant here. But if you see in the equation, our mathematical equation, where we use du and dw, both are there. They are not constant in case of adiabatic equation, right? So we'll be writing the entropy in change in entropy change in terms of specific heat, or let's say internal energy and volume terms or work done terms. Okay. Now, this will be our equation for an irreversible process in case of adiabatic process. But if they ask you in adiabatic process, what is delta Q? Nothing but it is 0. So delta S system for a reversible adiabatic process, compression and expansion in both cases, it will be 0. Okay. Now, any doubts until here? Until the expression of entropy? Okay. If you don't have any doubts, let's move to the next section. Next slide. The main section that is about Gibbs free energy. Okay. No. What is Gibbs free energy? Nothing but it is used to relate temperature, enthalpy, and entropy of a system so that you will get whether the reaction happens spontaneously or not. We know that if the enthalpy of a system is very high, it tries to come to lower enthalpy. And if the entropy of system is very low, it will try to go to higher entropy. So this is what we observe. And if we, regarding temperature, if we see, if you see reactivity, let's say at low temperature reactivity is less and at high temperature reactivity is high. So based on these three relations, we will be interconnecting all these three relations, and what is the final effect if you are using at different enthalpy, temperature, and entropy. So what is the final effect, whether the reaction or the combined effect of these systems can give you a spontaneous reaction or non-spontaneous reaction on a whole. We'll be seeing these cases now. First thing we'll be talking about spontaneity itself. Gibbs free energy is nothing but it will say what is the spontaneousness of a reaction, whether it will occur on its own or whether we need to provide some kind of energy to the system so that the reaction may happen. First thing, spontaneity, as you know, higher temperature reactivity is high, the reaction occurs more easily, and lower temperature reaction occurs very slow. So the spontaneity is definitely depending on temperature, right? Second thing is enthalpy. What is the energy of the system? That is also there. Whether the reaction will be, whether the system is at higher energy or lower energy. That means at higher enthalpy or lower enthalpy. Now, next thing is entropy. Nothing but how the energy is distributed, not the exact energy itself, but how energy is distributed. So generally, the energy, what happens to energy is that according to whatever we observe in the nature, the energy tries to distribute in a large area rather than a particular point itself. We'll try to distribute more rather than a particular point. So that is what entropy is nothing but what is the energy distribution. So as the energy distribution increases, that is nothing but entropy is increasing. So these are the terms we'll be relating to define spontaneity. First thing is to calculate delta S universe, it is very much difficult. We cannot take the whole universe entropy at a time. So we'll be trying to see the spontaneity based on entropy of the system itself by removing the universe entropy, or we'll be seeing how to calculate the universe entropy indirectly without using the entropy of surroundings. We can calculate the change in entropy of system for sure, but the change in entropy of the surroundings, to calculate that, it is very much difficult. So that is the main reason why we cannot calculate delta S universe that easily. So what we use the delta S system itself, entropy change of the system itself, and how to calculate it indirectly to get our entropy change in universe. Okay. That is nothing but our Gibbs free energy. Now, a system parameter to predict the spontaneity of a chemical reaction was introduced by Gibbs. Okay, he predicted how to interpret a spontaneity of chemical reaction. Okay, so that entropy calculation for the surroundings is not needed. So as we cannot calculate the entropy of surrounding, change in entropy of the surroundings that easily, and indirectly it affects the entropy of the universe also, right? So how to calculate the change in entropy of the universe, that is total entropy, without calculating entropy of surroundings. That is our main concept here, or how to do that is our main concept. First thing, let's see, it is a property of system, Gibbs free energy, represented with capital G. Okay, it is represented with capital G, and it's a property of a system. Now, Gibbs free energy, Gibbs give this equation, this mathematical equation, to relate enthalpy, temperature, and entropy of a system. That is, G is equal to H minus T delta S, T into delta S. Okay. This is the expression, mathematical expression given by Gibbs. Now, this is a state function. It doesn't depend whether you are achieving in a single step or two steps or 10 steps. Either you go to 10 steps or single step, the change in Gibbs free energy will be same. Okay. That is not a path function. It is a state function. It doesn't depend on what path you are choosing. Next thing is Gibbs free energy is a extensive property. What does that mean? That means it depends on how much amount of substance you are taking. If you are taking 1 mole of substance, break the bonds, it has different energy. If you take half mole of substance to break the bonds, it have different energy. So the same way here also, Gibbs free energy also depends on how much amount of substance you are taking, whether it's 1 mole or 2 moles or half mole, based on that. Okay. Now, this is nothing but a general expression here where delta G of a reaction, but the change in Gibbs free energy of a reaction is nothing but change in Gibbs free energy of the products minus change in Gibbs free energy of the reactants. Okay. Simple reaction, but you can get the problems from here also. Nothing but you need to do what is the energy of the products minus what is the energy of the reactants. Gibbs free energy of the products minus Gibbs free energy of the reactants. Now, this is a mathematical energy equation which was given by Gibbs, right? No. What we'll be doing, we'll be using this mathematical equation so that we can derive the equation which we can say whether the reaction is spontaneous or whether reaction is non-spontaneous without calculating the entropy of the surroundings. Okay, that is what we'll be seeing here. Now, by using this equation, let's say we are taking initial terms as G1 is equal to H1 minus T S1. Okay, at constant temperature, we are taking these are our initial conditions. And let's say we are taking G2 is equal to H2 minus Ts2. Nothing but keeps said final conditions. These are at our final conditions. Okay. So generally, you know that entropy or enthalpy, these things we cannot calculate at a particular point itself. So what we do, we'll be taking an initial position of a system and final position of system, and then we'll be calculating what is the change in or the what is the difference between these two. What is the energy difference between these two positions? So the same thing we'll be doing with Gibbs free energy also. What? So if we do that, what will happen? Where delta G is equal to delta H minus T delta S will be getting. Nothing but G2 minus G1 is equal to H2 minus H1 minus of T into S2 minus S1. Right? This is we are writing in terms of this one. Now, delta G is equal to delta H minus T delta S is known as Gibbs-Helmholtz equation. Gibbs-Helmholtz equation. Okay. Now, this is the equation we derive, and by using this equation where we cannot calculate the total entropy of the universe, so that we'll be using a different method to calculate total. Now, first thing, you know that delta S universe is equal to delta S system plus delta S surroundings, and we cannot calculate delta S surroundings, so that we cannot calculate delta S universe completely. So, how to find out delta S surroundings instead, without directly find out delta S surroundings? Now, to do that, what we consider is first thing is we'll be considering the reaction at constant temperature and constant pressure. Okay, there are the two conditions what we'll be considering first, and let's say QP amount of heat is given by the system to the surroundings. Okay, okay, clear. These are the two assumptions we are taking here. Now, in that case, if I ask what is the change in or what is the heat gained by the surroundings at constant pressure, is equal to nothing but how much heat is lost by the system, right? Nothing but I can write as minus of heat lost by the system. Yes or no? Right. Now, now at constant pressure, what is heat? Nothing but enthalpy. We have seen that, right? So I'll be writing it as minus delta H system. Minus delta H system. We have seen this, right? Where delta Q is equal to nothing but delta H at constant pressure. Now at constant volume is nothing but delta Q is equal to delta Q. So here we are using at constant pressure. So delta Q is equal to delta H of the system itself. Now, if we take this as our first equation, now if we take this one as our first equation, and if you see delta S surroundings is equal to QP surroundings by, right? Now, by using this equation, what we can write instead of QP surroundings, we'll be writing as minus delta H system. Okay, we'll be writing it as where employs delta S surroundings SURR, I'm writing it as, and that is equal to minus delta H system by T. Okay, just substituting the values, nothing more here. Now, if you take this our first equation and the change in enthalpy by temperature for Q surroundings, delta S surroundings is nothing but our second equation. Okay, note on the points properly. No, if that's the case, no. By using first equation and second equation, what we are getting delta S total is equal to delta S system minus delta S surroundings. Instead of delta S surroundings, I'm substituting directly the delta H system by T. Okay, by using first and second equation, I'm combining those so that we are getting this equation. Now, if I rewrite this equation, let's say I'm changing the negative terms to the other side. That means I'm getting minus delta S total and minus delta S system plus delta H system by. And if I multiply with temperature, what happens? This third equation, that will be getting as T minus T delta S total is equal to minus T delta S system plus delta H system, right? Now, if we take this one as our third equation, if we take this one as our third equation, okay, nothing but minus delta S total is equal to minus delta S system plus delta H system, okay. Now, if we use this third equation and substitute in case of delta G, what is delta G? Nothing but delta G is equal to delta H minus T delta S, right? If I take it for system delta G system, delta H system minus T delta S system, exactly this case, right? Exactly minus T delta S plus delta H minus T delta S. So if we substitute this total thing, we'll be getting the entropy in terms of minus T delta S total. So indirectly we have calculated the entropy of the universe itself. Now, what is the second law of thermodynamics saying? That entropy of universe is always increasing, right? You know that. So if we substitute all this value according to Gibbs-Helmholtz equation, delta G is equal to delta H minus T delta S, and by using our third equation, if we are substituting it in the delta G system equation, what will be getting? Delta G system is equal to minus T delta S total, right? Just I'm directly substituting delta H system minus T delta S system as minus T delta S total by using our third equation, right? Now, if I do this and you know that for a system that is delta S total, that is delta S of the universe is always greater than zero, right? What does that mean? What is this whole value is equal to? This will be always negative. Now, if this value is negative, delta is positive, change in entropy is positive, and minus T delta is negative. What does that mean? The the Gibbs free energy is negative. What does if Gibbs free energy is negative? That means it gives us a spontaneous reaction. If T delta is positive, minus T delta S will be negative, and delta G will be always less than zero. That is negative. If this is the situation, the reaction will be spontaneous reaction. Okay, this is what we learn here for today. Now, the same thing. What are like terms we have learned till now? First thing is delta H, delta G is equal to delta H minus T delta S. And what was the other thing we have learned? That is minus T delta S of universe or total. We cannot calculate delta S of universe. So what we did, indirectly we calculated delta H system minus T delta S of system. By using this, we calculated the delta S universe indirectly. So these are the two main equations you need to remember here. And you know that dq at constant pressure is equal to dh. Try to remember these. Okay. Now, let's see what happens to the reaction and when it is spontaneous, whether the entropy is positive, delta G will be positive or not. Yeah, for a system we are calculating here where delta G system is equal to delta H system, I'll print as SYS, minus T delta S system. Now, whenever the change in entropy for a system is positive, that means T delta S is negative. And if delta H is having very high energy and positive energy, let's say, that means the reaction is spontaneous reaction as delta G is negative. Okay. Now, if we are talking about equilibrium case, then the change in Gibbs free energy will be zero as the forward reaction and backward reaction is same. So that's the only reason why delta G is equal to zero in equilibrium case. Don't forget this. Generally in questions, they'll be mentioning equilibrium and they'll not mentioning Gibbs free energy value. So at that time, you need to take the Gibbs free energy value as zero. Now, for a non-spontaneous reaction, what will be zero? The Gibbs free energy will be positive, and for spontaneous reaction, it will be negative. Okay, clear with the terms. Whenever equilibrium is there, change in Gibbs free energy is zero. Whenever spontaneous reactions are happening, change in Gibbs free energy will be negative. Whenever non-spontaneous reaction is happening, change in Gibbs free energy will be positive. Now, let's see different cases whenever enthalpy is positive or negative and entropy is positive or negative, and what happens to temperature if these two cases are different. First thing, let's say enthalpy is positive. Okay, enthalpy is positive. That is equal to positive minus of what should be the T delta S value if you want to be delta G as a negative. Nothing but delta S should be positive, right? But here delta S is given as negative. Now, if both are negative, that means negative into negative, that will give us positive. So here delta G will be equal to a positive sign. If delta G is positive, the reaction will be non-spontaneous, right? The reaction will be non-spontaneous. Try to see this, okay? Next, if delta H is negative and delta S is positive, what is the T minus T delta S value here? One second. Let me turn on the charger. Let's continue. If delta H is negative and delta S is positive, then what is the minus T delta S value? It will be negative, right? It will be negative. What happens to delta G value? It will be negative. As both are negative, it will be negative and the reaction will be spontaneous reaction, right? The reaction will be spontaneous reaction. Next, if delta H is negative as well as delta S is negative, then what happens? Delta G will be maybe positive or maybe negative. Why? The only reason is T delta is positive. That means it should be more than delta H. Then only it will be, the delta G will be positive, right? So there are two cases whenever delta, this positive value, if it is, let's say we are taking -1 and here +2. Then what happens? The overall answer will be +1 where delta G is positive. Now let's say the second case, if enthalpy is -2 and delta minus T delta S is +1. Then what happens? You'll get -1 where the delta G is negative. That means the reaction is spontaneous. So in this way, you'll be getting two possible cases. So at lower temperature, the reaction is spontaneous, okay, where the T delta S value will be less at lower temperatures. Now, if we use higher temperatures, that means the product of T delta S is very much high, which can overcome enthalpy at higher temperatures. So at this point, what happens? The reaction may become non-spontaneous. Okay, just remember this: at high temperature, what is happening; at low temperature, just substitute the values in the formula, you'll get the answers. Don't worry. Now let's say both are positive. Then what happens? That means enthalpy is positive, but T delta S is negative, right? What does that mean? If the product of T delta S is more than the positive value of enthalpy, then delta G will be negative. Let's say if the product of T delta S is less than the enthalpy value, then the delta G will be positive. Here also both conditions are possible, right? But here what you need to see, that means if T delta S product is more, it will give you a spontaneous reaction. Exactly opposite in the previous case. Okay. At lower temperature, as T delta S product is less, the reaction is non-spontaneous. But as we go to higher temperature, as the product of T delta S increases, the spontaneousness increases. As the delta G attains negative value, the spontaneous nature will be increasing. Now, are you clear with the concepts? If you have any doubts, try to clarify it now. Okay. If you don't have any doubts, let's move to the next section. First thing, above what temperature the following process would not be spontaneous, where we are converting a gas into a liquid. Okay. Where delta S is given as minus 50 joule per Kelvin per mole and delta H is given as minus 20 kilojoule per mole. Okay. So take your time, 2 minutes, and try to do the problem. Simple. Just substitute in the values. Have all the values. Is asking at what temperature the following process would be non-spontaneous. What you need to see, the product of T delta S should be more positive than delta H. That is what you need to see here. Just find out the product of T delta S, that is exactly over 20,000 kilojoules or 20,000 joules. That will give you the answer, right? Simple. Just you need to see what I should multiply 50 with. That will give you 20,000 or more than 20,000. Exactly. No. For a spontaneous process, delta G should be, sorry, for a non-spontaneous process, delta G should be positive, right? Now, if that's the case, just substitute the values in this case, right? Where minus 20,000, given T into minus 50. Now, you'll get a positive 50T. And if you do 20,000 by 50, that you'll get, the temperature should be at least 400 so that the reaction will be non-spontaneous. Okay. Now, the question, second question, try to do this also. Take a 2 minutes and do the question. Then I'll launch a poll. Try to answer in the poll. No, let's continue. I think you have done with it. Let's discuss what is the correct answer here. Okay. Now, what is given first thing? Find whether the given reaction is spontaneous at 1 atmosphere and 298 Kelvin, he is asking. Now, heat of enthalpy of formation of reaction is given. Exactly. This enthalpy is given, right? That is nothing but minus 127 kilojoules per mole. And is also giving standard enthalpy, standard entropy, not he's giving standard entropy, that is of AgCl, Ag, and Cl2. He's giving all. If you want to find out the entropy of the reaction, then what you need to do? Nothing but products minus reactants, right? You have products entropy as well as reactant entropy. So try to find out. You also know the temperature. What you need to do, just find substituting in delta G, where delta H is already given minus T delta S, where all are at standard conditions, and delta S is nothing but delta S naught. If you want to find out, that will be summation of entropy changes for products minus summation of entropy changes for reactants. This is what you need to find out. Simple, right? Just substitute the values where 96 minus the entropy values of the reactants. No, why we are doing it half exactly? Why? Because we are using it like the half mole. You want to break half mole of the Cl2 bonds, you need exactly half of that energy where we required exactly for 1. That is what we need to see. That is the only reason why enthalpy is or entropy is a extensive property, not a intensive property. Now, if you substitute the values where delta G naught is equal to H naught minus T delta S naught, that will be equal to 10, 109 kilojoules per mole. Exactly, nearly. Okay. Note on the answer. If you are done, let's see the next question where the process is spontaneous in this equation, right? No, let's see standard Gibbs free energy. When the reactants under standard conditions, like you have seen the standard Gibbs free energy and standard Gibbs free energy. What is the difference here? The only difference is regarding how many moles of the reactants or products you are talking about, and what is the temperature and what is the pressure we are talking here. Okay, that's the only thing we need to see. When the temperature, when the reactants under standard conditions gets converted into products, which is also under standard conditions, then the free energy change is known as delta G naught. That is why in the standard conditions will be representing this not conditions. Okay, no. What we write delta G naught of a reaction is nothing but delta G naught products minus delta G naught reactants. Okay. Now, if that is the case, we can write as if n number of products and n number of reactants are there, sum of standard free energies of formation of products minus sum of standard free energies of formation of reactants. Okay, here also standard, not only free energies, standard free energies. Okay. Now, let's relate a important concept, that is how to relate equilibrium reaction with Gibbs free energy and equilibrium constant of a reaction. First thing is, this is our equilibrium which we'll be considering. If you want to write equilibrium coefficient for this equation, how to write? Nothing but concentration of the products by concentration of reactants. If there are n number of moles, that is concentration of products, power that, as we can see here, concentration of B power B moles and concentration of A power A moles. Okay. This is nothing but a reaction coefficient at equilibrium. If it is equilibrium, nothing but Q is represented as K equilibrium. Simple. Just you need to substitute this in Gibbs free energy. Now, we know that delta G is equal to delta G naught plus RT ln Q, right? Now, in this equation, what we need to do, just substitute the reaction coefficient value here. If it is equilibrium, keep Q as K equilibrium, okay? At K equilibrium, what is the standard, what is the Gibbs free energy change for a reaction? Delta G will be equal to 0, right? At equilibrium. At equilibrium, delta G will be equal to 0. This is the main point you need to remember here. Okay. Note this down. This will not be given. Whenever they say equilibrium, delta G will be 0. Not the delta G naught at standard conditions, the delta G of the reaction itself. Now, that is the case. Just rearrange this formula where delta G is equal to minus RT ln Q, right? Just rearranging directly where delta G naught is equal to minus RT ln K equilibrium or Q. If it is not at equilibrium conditions, then delta G will also be there. If I elaborate the natural logarithm, that will give us delta G naught is equal to minus 2.303 RT log K equilibrium. Okay, this is the main equation. Directly questions will be given here also, where equilibrium constant will be given or concentration of the products and reactants and number of moles of the products and reactants will be given, so that you can calculate K equilibrium and you can derive the delta G naught, standard Gibbs free energy value. Okay. Are there any doubts still now? If you have any doubts, try to text in chat. Okay. If you don't have any doubts, let's move. The only thing you need to remember here is nothing but first reaction, that is delta G is equal to delta G naught plus RT ln Q. This is our main equation. And only at the equilibrium conditions where delta G is equal to 0. So that we'll be rewriting this equation in this form. That is delta G naught is equal to minus R 2.303 RT log K equilibrium. This is the only thing here. If any different reaction is given, let's say a reaction is given in this way, where P plus Q NP plus MQ. Let me write it again. NP plus MQ gives rise to XA plus YP. Now, what is the reaction coefficient? Q is equal to nothing but concentration of products first, A power moles into concentration of B power Y by concentration of P power N into concentration of Q power M. Just how many products and reactants are given, based on that you can write the reaction coefficient. Okay. No, the applications are we use this delta G naught value so that we can calculate enthalpy and entropy value indirectly, right? If you know delta G naught, you can calculate enthalpy or entropy also. Now, one more point is, if K equilibrium is measured in laboratory, delta G naught can be measured. That's what we are saying. If you can find out the equilibrium constant of a reaction, then automatically you will be finding the Gibbs free energy of a reaction, standard Gibbs free energy of a reaction. Now, try to do this problem. Take 2 minutes and try this problem. The equilibrium constant for a reaction was found to be 10 power 5 at 300 degrees centigrade. Note on this as at 300 degrees centigrade. Now, find the standard Gibbs free energy for the reaction. Equilibrium constant is given. Temperature is given. Can you find out the Gibbs free energy? Take 2 minutes and do the calculations. I'll launch a poll. Hope you are done. First thing, keep in mind what is given. Write down first. Nothing but he's saying equilibrium constant. That means already delta G is equal to 0. Okay. And he gave equilibrium constant is equal to 10 power 5. And temperature is given, that is 300. 300 Kelvin. Sorry, not degree centigrade. It is 300 Kelvin. Okay. 300 Kelvin. What you need to do, just directly substituting it in delta G naught is equal to minus RT ln K equilibrium. Just substituting in this equation, you'll get the answer, right? Now, R value, when you are taking it in energies, try to take it in joules itself. That is 8.314 joule per mole per Kelvin. Substitute the value, the answer will be minus 2.28.7 kilojoules. Okay. Gibbs free energy will be minus 28.7 kilojoules. No. Last concept, that is third law of thermodynamics, and direct simple questions will be coming on this. Okay. Where you need to remember what is the definition here. simple thing. What does third law of thermodynamics says that whenever you take any liquid or anything to or a solid, we prepare a solid at 0 degrees, 0 Kelvin, not 0 degrees centigrade, 0 Kelvin. Absolute zero we'll call it as 0 Kelvin is called as absolute zero. Okay. Now what happens here is as when we approach 0 Kelvin, the all the atoms will be converted into solid first, and these atoms will not even have a vibrational energy also. It will not even move from the place wherever it is. That means the energy of the system will become zero whenever we attain 0 Kelvin. But in reality, that is not easy or not possible that easily. Okay. Note on the definition of third law of thermodynamics, that is entropy of pure crystalline substance at 0 Kelvin approaches zero. That is nothing but absolute zero, 0 Kelvin. Okay. At that absolute zero, entropy or anything else of a system will be zero. So in this way, they'll be packed tightly without any movement in a perfect way, without any disturbance. Okay. But everywhere disturbance is possible, everywhere thing is not perfect, right? At 0 Kelvin, no disorderness, that is disorderness S is equal to zero. Now, as we increase the temperature, some disorderness will increase. There we'll get some kind of entropy as we go from away from 0 Kelvin. So if you see at room temperature, everything will have certain amount of disorderness for sure. Either it may be vibration or something else. Okay. Now let's quickly summarize whatever we discussed till now. The measure of degree of disorderness or randomness in a system is called entropy, and delta S is equal to Q reversible by T. We have seen different forms of delta S also, right? Where at constant pressure we have seen delta S is equal to delta H, and at constant volume we have seen delta S is equal to delta U. These we have seen. Yes or no? So try to see where we can use what. Delta H is equal to NCP dt, and delta U is equal to NCV dt. These things we have seen. Try to see where you need to substitute which formula. Okay. And then we have seen delta S, delta G is equal to delta H minus T delta S, this form. And at equilibrium what? Delta G is equal to 0. Okay. Delta G is equal to 0, not delta G naught. Okay. And you know that we cannot calculate delta S total completely all the times. So what we'll do, we'll be using a indirect method so that we can calculate delta S total or Gibbs free energy. Gibbs free energy of a system is maximum work that can be extracted from any system. Okay. That delta G will be giving you what is the maximum work it can be doing. The system can be doing on the surroundings. Okay. Delta G naught is equal to minus 2.3003 RT log K equilibrium. Nothing but relation between Gibbs free energy and K equilibrium. Okay. Now, what does third law of thermodynamics say you? Nothing but it say you entropy of pure crystalline substance at 0 Kelvin approaches zero. What does second law say you? Nothing but second law says about entropy. Now, what does first law say you? First law says you about energy. Energy of energy cannot be created nor destroyed, but we can convert it one form to another form. But entropy, can we create entropy? Yeah, we can create entropy. We cannot destroy it. Okay, that's what you need to remember here. And one more law you need to know is zeroth law. Zeroth law or zeroth law, like that. Now, whenever let's say we are taking three objects, A is there and B is there. Okay, A is there and B is there, and one more is there attaching both A and B, that is C. Now, if I say A and B is in equilibrium and B and C is in equilibrium, now that means that A and C is also in equilibrium. Simple. So if three systems are there and two systems are in equilibrium with each other, that means all the systems are equilibrium in the third system also. That is the only concept of zeroth law. If you have any doubts, you can clarify any doubts in the class, today's class. If you don't have any doubts, try to see these questions and solve these questions. Okay. If you don't have any doubts, you can leave the class. So tomorrow we'll be seeing few questions on thermodynamics. Just we'll be going through the application part. Now, this is all about thermodynamics till now. If you have any doubts, try to clarify. If you don't have any doubts, you can leave.